In this video, we will discuss the difference between equilibrium constants that are written in terms of concentration and those that are written in terms of pressure. In our previous video, using ICE tables to determine equilibrium concentrations, you may have noticed that the equilibrium constant listed did not have any units. That is because equilibrium constants are unitless. Now, it might strike you as bizarre that a value that has an equation that uses units in it would be unitless. So our equilibrium constant is equal to the product concentrations raised to their respective powers divided by the reactant concentrations raised to their respective powers. But the value for the equilibrium constant itself does not have units. The reason for it is that there are actually hidden units in our equilibrium constant equation. The equilibrium constant has reference values that we will technically be dividing our concentrations by. The reference values are 1 mole per liter. Later in the semester, when we're talking about electrochemistry and standard states, this will become more clear why we are using 1 mole per liter. But let's say we have a reaction of A of A plus B of B goes to C of C plus D of D. The way we would write out our equilibrium constant expression would be K sub C. The C here is used to denote that the values that we will be using are in terms of concentration using moles per liter. So we write out our concentrations, moles per liter, divided by our reference value, which is 1 mole per liter. What this does is it cancels out the units, so that the value that is being raised to the respective coefficient actually here has no units, which enables our K value here to have no units. The net effect is, because we are canceling out the units, in each one of our parentheses here, Kc has no units, though we do need to make sure that we are plugging in units into our values. So we need to make sure that we are plugging in concentrations in terms of moles per liter, because Kc explicitly has units in the equation of moles per liter. It has reference values that are used in the equation. Equilibrium constants for pressure also are unitless. However, there is a bit of difficulty that arises from the fact that pressure has many different units that are used, such as atmosphere, torr, millimeters of mercury, bar, and Pascal. They would all give different values for the equilibrium constant. The reason that, again, our equilibrium constant is itself unitless is because there are hidden reference values that are used to remove the units from the values that we're plugging in. The standard reference currently, according to SI units, should be 1 bar of pressure. 1 bar of pressure is 750 torr, 750 millimeters of mercury, 0.9869 atmospheres, or 10 to the 5th pascals. So if we take our pressures and divide it by these units here, we would end up converting them into bar, and then we can use them into our Kp values to come up with our equilibrium constant. Now, your textbook, the TRO textbook, ends up actually using atmospheres. This is unfortunately an outdated system that was abandoned in the early 80s. However, when you're working on problems in the book or in the associated homework, make sure that you're plugging in values in 1 atmosphere, because that is what is expecting. We can actually convert between Kc and Kp, and it involves doing a conversion between pressure and concentration. We do this by using our ideal gas equation. PV equals nRT. Now, there's a couple different ways of expressing this. We can think that our concentration has units of moles per liter, which means that it is an expression of N over V. If we rearrange our ideal gas equation, N over V is equal to P over RT. We could also express our ideal gas equation in terms of pressure, right? So pressure would be equal to N over V times RT. And this N over V is concentration, so this is equal to our concentration of, let's say, our A component times RT. Right? So this is the concentration of whatever we're interested in. We can work through a problem similar to what we've been using before. Let's say we have our standard equation, A of A plus B of B goes to C of C plus D of D. Our equilibrium constant in terms of pressure, our Kp value, as we would normally write it, would be pressure of C raised to the C power times pressure of D raised to the D power over the pressure of A raised to the A power times the pressure of B raised to the B power. Now, if we put in our hidden units of the reference pressures, this would be pressure of C over P ref, the reference pressure, that whole quantity raised to the C power, times the pressure of D over P ref raised to the D power, divided by our pressure of A over P ref raised to the A power times the pressure of B over P ref raised to the B power. We can now take our expression that we have here for concentration and how that relates to pressure and replace each one of our regular pressure values with a similar expression using concentration. We can replace this with concentration of C times RT over P ref raised to the C power times the concentration of D times RT over P ref, our reference pressure, raised to the D power, divided by the concentration of A times RT over P ref, our reference pressure raised to the A power, times the concentration of B times RT over P ref raised to the B power. Now you might notice that there's this repeating pattern of RT. We have essentially a repeating pattern here in each one of them that has an RT over P ref. We can actually pull this out, giving us our Kp value is equal to the concentration of C raised to the C value times the concentration of D raised to the D value over the concentration of A raised to the A value times the concentration of B raised to the B value times our quantity where we are pulling the RT over P refs out. So this would be RT over P ref to the C times RT over P ref to the D divided by RT over P ref to the A and RT over P ref to the B. Now there's a rule that comes along with exponents that if you have the same thing raised to an exponent. If they're being multiplied, it's the same thing as adding the two exponents together. And if you're dividing, it's the same thing as subtracting the exponents. So this part here is actually equal to the concentration of C raised to the C, concentration of D raised to the D, over concentration of A raised to the A, concentration of B raised to the B. And then what's in the set of parentheses here, we can re-express as being times the quantity RT over Pref, our reference pressure, which again is 1 bar, times C plus D minus what's on the bottom, A plus B. So we take the top minus the bottom. This value here we will represent as the change in the number of moles of our gas, right? Because essentially it's the change in the difference between the number of gas molecules. It's the number of gas molecules in our balancing chemical equation for our two products minus the number of moles of gas in our balanced chemical equation for our reactants. Okay, so this part here is looking a lot like Kc, but it is not technically Kc yet because we don't have our hidden units of our reference concentration. So we're going to take our Kp, multiply it by 1, and that 1 is going to be the reference concentration divided by the reference concentration. So we're going to essentially take our Kp value, multiply it by C0 over C0, our reference concentrations. This will give us concentration of C over C0 raised to the C times the concentration of D over C0 raised to the D divided by the concentration of A over C0 raised to the A times the concentration of B over C0 raised to the B. Now, in order to take into account all those various values where we were raising it to the different respective powers, our C0 that would be in the numerator, when we were doing this C over C0, multiplying by 1, this part here would need to be C plus D minus A quantity, A plus B, which is our delta N gas, right? This here is the exact same as we had over here. We would also need to multiply this by our RT over Pref raised to our delta N gas. So the term here, this, inclusive of our C0s, is Kc. We can take this term here, it's raised to the exact same power as this, and so we can move it inside. And what we're left with is Kc times C0 times RT over Pref times delta N gas. Now, the important part here is both Kp and Kc are unitless, and so our conversion factor, which is located right here, needs to also be unitless. So our Pref value here has to have the same units as the R, and the C0 here is used to get rid of the moles per liter. So our R value needs to be in terms of the same unit as our Pref, which for our case is going to be bar. However, in the Tro textbook, that would be atmospheres. Our C0 is going to be moles per liter, and so the R value that we're using here needs to have units that match the C0 and the Pref. And so it needs to be in the case of our work, bar liter per mole Kelvin to get all the units to cancel out. In the case of TRO, instead of bar, you would use atmospheres. So we need to make sure that the R value that we're using agrees with the reference pressure and reference concentration. This whole thing ends up cleaning up because our C0 value is 1 mole per liter. So essentially we're taking RT times 1. And our Pref is 1 bar. So essentially we're dividing by 1. So our C0 and our Pref don't actually change the term that's inside our parenthesis. What their purpose is to get rid of the units. This delta N gas is the number of moles of gas that we have in our balanced chemical equation up here of our products minus the number of moles of gas in our reactants in our balanced chemical equation. So that would be C plus D minus the quantity A plus B. A more cleaned up form that you will see if you're looking on the internet or in your book is this form here. Note, however, that this is not including or does not show the hidden units, but the hidden units are there to make this RT value unitless, right? So if you take something that is unitless and you multiply it by something that has units, you'd have to have units. So this component here, this RT, needs to be unitless. And that's what those reference concentrations that we see over here do. Let's look at a problem, how we can convert between Kc and Kp. So we have a reaction listed below. SO3 goes to SO2 plus O2. And we have a Kp value at a particular temperature. Now, our equilibrium constants are temperature dependent, so the only way that we can do this is if the two values that we're trying to compare are at the same temperature, which they are. So the reaction below has a Kp value of 3.3 times 10 to the negative fifth at 700 Kelvin. What is the value for Kc for this reaction at the same temperature? So we're going to start with our end expression that we just came up with, which is Kp is equal to Kc times quantity RT to the delta N gas, right? Products minus reactants. So first thing we need to do is figure out what our delta N gas is. So delta N gas is equal to the number of moles of our gas in our products minus the number of moles of gas in our reactants. So that would be 2 from our SO2 plus 1 from our O2. That is the sum of the number of moles of our gas from our balanced chemical equation minus 2 from our SO2. So this would be equal to 1. So in this case, our delta N gas is 1. Now, we have Kp, we want Kc, so we need to rearrange this equation to get Kc by itself. So we will divide both sides by our RT to the delta N gas. RT to the delta N gas. Okay, on the right-hand side, the RT delta N gases cancel out, giving us an expression that relates Kc to Kp, trying to solve for Kc. So Kc is equal to Kp divided by our quantity RT to the delta N gas. So plugging in our values, this is 3.3 times 10 to the minus 5. Note it has no units. The R value we will be using is we need the units to be bar liter per mole Kelvin in order for all of our units to cancel out. And so we will be using the 0.08 314 liter per mole Kelvin. We're going to multiply this by our temperature in Kelvin, 700 Kelvin. The Kelvin cancel out. And if you remember, this actually has C0 and Pref in it, and that is what will end up actually canceling out our bar and our moles per liter, or well, liter over mole. We're going to be raising this to the delta N gas, which would be raised to the first power. And so this is equal to 5.6703 times 10 to the minus 7. There are no units. In terms of significant figures, this value here, our Kp, has 3, assuming that our temperature actually has 3 significant figures to it. Our end answer would have 2 significant figures. So our answer would be 5.7 times 10 to the minus 7. That would be our answer. Note that it has no units, right? Because this is an equilibrium constant. This is Kc being equal to that value. Our equilibrium constant expressions are interested in looking at how our equilibrium concentrations are related to each other, keeping all the constants to one side and all the variables, which are our concentrations, to the other side. What this means is that the concentrations of pure solids and pure liquids are not going to be included, and that's because the concentration of a pure solid or a pure liquid does not change during the course of a reaction. If we were to use up half of our solid, the number of moles would decrease in half, but so would the volume, and so the ratio stays the same. Same with our a pure liquid. If we use up half of our liquid, the number of moles would decrease by half, but so would the volume. And so the ratio of moles per liter would stay the same value, so it becomes a constant. Solids and liquids are also incompressible, meaning that if we try to compress them, they do not change in volume. So their values for concentration are constants and therefore get lumped in with the other constants. So because their concentrations don't change, solids and liquids are excluded. They are not included in our equilibrium constant expression. So let's say we have our reaction here. Carbon dioxide reacts with water. Note the water has an L. This means that it's a pure liquid. So CO2 reacts with water to form H plus aqueous plus HCO3 minus aqueous. The equilibrium constant will be our products over our reactants raised to their respective powers, leaving out pure solids and pure liquids. This water gets left out of our equilibrium constant expression. The reason it is left out is because it's a constant, which means it already appears over here. It is lumped into our Kc value, right? So if we were to include it here, we would be double counting it, which we don't want to do. So all constants get lumped in with our constant. All the variables appear over here. The concentration of water as a liquid is a constant, and so it will not appear on the right-hand side. Instead, it is lumped in with our Kc value. Now, the way that equilibrium constants are actually measured, well, the most direct way is by finding the equilibrium constant through the measurement of the amounts of reactants and products in a mixture once it has reached equilibrium. So what you would do is you would set up your reaction and keep measuring the concentrations until they remain the same, until they are steady. That would tell you that you're at equilibrium. You can then take the concentrations of the products raised to their respective coefficients divided by the reactants raised to their respective coefficients, and you would have your equilibrium constant. The equilibrium mixtures may have different amounts of reactants and products, but the value of the equilibrium constant will be the same as long as the temperature is kept constant. So as long as you don't change the temperature, the equilibrium constant is a constant value. It will not change. The value of the equilibrium constant itself is independent of the initial amounts of the reactants and the products. As we saw when we were looking at the system of hydrogen gas and iodine forming hydroiodic acid several videos ago.